Recording is on. So we are engaged in the experiment of trying to live stream and record for later viewing of CS 436V at the start of online classes at UBC. So, welcome to virtual classes, everyone. I hope that you are all as safe and sound as possible given the situation, which is complicated and perhaps rather scary. But I'm glad to see that many of you are joining for the live stream. Going to the slides. The news is we are in online mode. Everyone who is joined by Zoom obviously has found that. I see a hand raised. One sec. Yes, you're unmuted, Harlan.
Can you hear me?
Yes, I can hear you.
Okay, I think your screen is still frozen.
Aha!
And also, there's some questions in the chat. I don't know if you see that.
I see. Okay, so now I have unfrozen my screen share. So thank you for noting that. And let me find the chat view, which I hadn't even, let's see. Oh, Zoom. Hold on, maybe it's up here. Where is chat? Here we go. Aha. I see. I'm going to not have the chat on the main screen that's being recorded, but now I can in fact see it. There we go. Okay, so people can now hear me. I see the chat. Yeah, so answering some questions. Is this link going to continue into office hours? What I'm going to do is briefly, so I'm going to use the same Zoom URL for that, but I'm going to restart it in a different mode. Right now, everyone is able to just connect. In office hours mode, there's this whole waiting room feature so that I can have private conversations with people if they want to discuss things like their own grades or their own projects. So it will be the same URL, but I'm going to disconnect and reconnect because I have to redo some settings. And the question of why did I choose Zoom over Canvas Collaborate Ultra? Because I know Zoom well and I've been using it for 1.5 years for all kinds of meetings. And there's enough chaos in the world that I'm not going to try to learn Canvas's Collaborate Ultra. We might end up using that for some other thing, but just for the current live streaming, we're going to go with what's familiar to me. Okay, did it just become really laggy? Good question. Looks like it's just that one person. Okay. All right, then I will remute so that everyone is back to muted. I think the show hands is working pretty well. It does let me know when that's happening. Okay, so as I said, for the office hours mode, I will be restarting the Zoom, so it'll be the same URL, but there'll be a mode where I explicitly let you in just to let people have private conversations. I did test out that waiting room feature. It seemed to work okay. Okay, so for the labs, they are going to be Zoom. We are also going to try to use the Canvas scheduling mode where you can actually sign up for an explicit block in advance. We're probably going to do 10 or 15-minute blocks of time during what's normally the lab hours. And then even if you didn't sign up for a slot, if they're not talking to anyone else, you can just join that Zoom to check whether they're available to talk. So it's sort of like going round robin in the room in labs, but with a little bit of sign up in advance. We had no idea how many people are going to want to. We know that it had been quite low attendance to labs in person, so we don't know if they'll be even lower by Zoom or perhaps many more by Zoom, given that you don't have to actually go out into the world. So we're going to see how that goes on Friday, possibly even shifting things on the fly. For the final exam, oh, I see some questions on chat. Will we still use Socrative? In general, yes, we will use Socrative in specific. there's some chance I might cut over to Zoom polls, but I think Socrativ's easier. I've already got the infrastructure in place. In specific, I don't actually have a Socrative poll today because I was getting everything else sorted out with all of the online stuff. So today will not be directly using Socrative unless I come up with something on the fly. Could be, but unlikely. Will we be able to access recordings after lecture? That is the plan. Let me double check that I did in fact remember to hit. Yes, I am recording. I do plan to post that after. Okay, so for the final exam, the one thing we know is it won't be in person, so you are free to leave if you need to. You don't have to leave campus. Last I heard, it was still staying open for those who want to stay. So I am, logistics-wise, could I address this Piazza post? Hold on, let me click on this Piazza post. Yes, the participation marks. What we're going to do, hopefully later this week even, is give you a sense of how those marks are. We've been recording all the Socrative marks all along. We're going to assemble those into a spreadsheet and also load in the stuff from the Piazza posts. So stay tuned later this week. We'll actually give you a preview of that. I have not actually written down what the exact ratio is on that, in part because I want to make sure we don't have any extreme breakdowns on getting that Socrative data in. So you will see more about that, hopefully within a day or two. Good. Yep. Okay, so let me get on to the next slide, which is what's going on with foundations. So schedule shift is due to the chaos. We're flipping things around just a little bit. There's not going to be a separate Foundations 5. Instead, I'm going to have combined content across what would have been both 5 and 6. So it's basically Foundations material for a lot of the base stuff. Specifically, that's going to be through, where's my schedule? So the Foundations 5 is going to be covering everything since Foundations 4 through rules of thumb. It will go out on Thursday, March 26th, and then be due the following Wednesday. So in terms of the amount of material covered, it's going to be more. In terms of the amount of time that we hope it will take you, it will be probably in the middle. I don't think it's going to be exactly double, but it might be about 1.5 times. So you have not missed a Piazza post. That is what I'm announcing now in class. I will do a follow-up Piazza post after the lecture's over, just to make sure everyone sees that, even if they didn't make it to class. So milestone 2 and milestone 3 are on schedule for milestone 2 next week, and then milestone 3 the last day, which is Wednesday, April 8th. So again, nothing is due this Wednesday. Too much scrambling as we adapt to this new world. Okay, so in terms of more news, the midterm marks and the solutions have been released. I really want people to make sure they know that what they see on Gradescope, which has the detailed breakdown, that is with respect to a number that's not 100. It's 75, which is the number of points that were in the exam, because you had 75 minutes to make it easy for you to track your time. So the number you see on Canvas is a percentage number, which is the one I typically sort of think about this as, and the mean was 79%. I'll have some more full histograms up on that soon, but we don't have those ready yet. But we do have a very detailed solution where you should be able to understand what rubric we were using for marking. There's a number of alternative answers, and in many cases we said, you know, here are 5 possible answers. Any one of them would have gotten full credit, and some explanations of things. So for milestone 1, we have also released those marks. Note, a number of teams we specifically suggest that you discuss things with us. We did give, of course, as usual, a bunch of written feedback, but in some cases, our answer was, hey, you should really come chat with us. So what does that mean? That means my office hours today are one possibility. It means the Friday labs are another possibility. It means making a specific appointment to talk to me about that if the office hour time is not convenient for you is yet another possibility. But what we really want to make sure is that you understand our feedback, and a lot of that was, in many cases, it was of the form, even if you do everything you're talking about doing, the scope doesn't sound right. For most of you, the scope is too small. I think there might be a few cases where the scope was dangerously large. But sometimes we wanted you to discuss with us for other reasons than just purely scope. But we want to make sure that you've got the feedback of, if you continue on the path you propose, are you lined up to do well? And in some cases, the answer was not quite. Let's make sure you've got the right scope. We've also got the P3 marks released. That distribution is rather bimodal. Let's go to the next slide. We are certainly somewhat concerned about the bimodalness of the P3, where there were a sizable number of people who did not do so well compared to a sizable group that did quite well. So here you can see P1, P2, and P3, and then the combined for all the programming assignments. So we really want to make sure that any of you who were struggling in P3 do have the support you need to get through the final project. And as always, we are open to, there's actually quite a few private posts on Piazza for people asking for specific help in places where they get stuck. That's great. That's one of the things it's there for. Just while I'm putting up histograms, here's a sense of how all the quizzes have gone now that we're done with quizzes. For most of the quizzes, almost everyone got pretty much everything correct across their 3 tries, although that was less true with that last quiz 7 than the others. So that was certainly an outlier compared to the rest. And then this is the combined marks for the foundation so far. In general, people are mostly doing reasonably well, which is great. So that is the roundup of the news. Before I move on to main new content for today, do people have questions? Checking for show hands. A point in the chat, you think the reason some people tanked Q7 is that the lowest gets dropped, so some people skipped it. Yeah, that's, or at least did it without huge amounts of care. That makes a lot of sense. Good thing to know that we didn't just miscalibrate that one. Any other questions or comments or concerns about the logistics of how we're doing all of this? Going once, going twice. Okay. Let's move onward and talk about aggregation. So just to get you to remember where we were last time, we had been talking about aggregation. We had ended up with this continuous scatter plot after talking through a lot of approaches to things like histograms and density plots and violin plots and box plots. So these were all ways to aggregate tabular data. Now we're moving on to talk about aggregating spatial data. So what's interesting about spatial aggregation is, well, it's hard. To be more technical about why it's hard, something that the cartographers have called MAUP, the Modifiable Aerial Unit Problem. And what that is a really big and fancy acronym for is saying that if you change the boundaries of these spatial regions that you have for geographic or cartographic data, you can get incredibly different results. So let's just look at this middle group. I believe you can see my mouse, so let's see if that's true. So here we have, notice how these yellow data points are the same across every one of these 3 views. But the background for those regions are shaded by density, that is the number of points in the region. Notice how the pattern you see, if all you saw was, if you were just seeing this as a heat map, if you didn't see the yellow dots, if you were just looking at this sort of heat map style view where you're color coding a region, you would have a dramatically different sense of what this data set was all about. So on the left, we've got one where one of those is considerably darker than the other in a way that looks like it might be a little bit of an artifact, in the sense that it just happens that the distribution of the actual items with respect to the zone boundaries give you that one very hot spot in the middle. And then notice how if we pick different boundaries, let's say instead of picking regular spatial grid, we've done something that looks more like explicitly planned cells. Maybe this is more like something like, say, a city would work versus the suburbs. And notice how in this one we see a really different picture. We've got these two dark blue ones that are near the center, and then the one slightly lighter blue. And then, so we very much have this idea that there is a center mass and then some outskirts. And then look at this one on the right. Now with this one, we do not have any sense of a dense central region. We actually have a sense that there's a sparse central region, and then a relatively equal density as we go all around, and that has to do with the way that we divided this up. So just like histogram bins are tricky, and you can get a different pattern with histograms if you have different bins. To remind you of what that looks like, let's find my bin size one here. Where's my histogram bins? Right, so noticing how we can see some slightly different patterns with different numbers of bins and histograms, this problem is even more extreme with this sort of spatial data. So this is the moral equivalent of changing bin size, but it's not just sort of a one-dimensional situation. We've now got something two-dimensional with this sort of 2D spatial data. And then in addition, so what they call zone effects are this idea of the region boundaries can have major issues, even if all those regions are roughly the same size. And then what they call scale effects is this problem that as you aggregate up, so as you go from larger regions to smaller regions, you might also see some really very different visual patterns. Here is, I believe it's Indiana, where we're seeing county level versus, or sub-county level on the right, versus full county on the left. And we're seeing some extremely different kinds of patterns because of the scale of the data. So there are most definitely a lot of challenges with spatial aggregation. The one that typically gets the most press is what's called gerrymandering. That's actually named after a long ago Congress politician in the US. And this is when people essentially are exploiting this problem with the direct goal of political gain. We actually saw a gerrymander map back when I was showing you a small multiples map. It was showing you the shape of some geographic regions that were used for voting. And so this is a useful example of how, first of all, it's a tricky problem. At a meta level, these are visualizations of visualization. These are trying to show what is going on with gerrymandering. So the example here is if you've got some region with 50 people and you've got 60% blue, 40% red, and you are actually dividing this up, there are ways of trying to actually capture that underlying percentage that do well. Now, notice how you actually have a distribution of winners in the district that correspond with the underlying population counts. However, notice that these spatial regions are not compact. They're actually long, thin stripes. It's often desirable to have compact spatial regions, but notice how there's a way to do that here, where you're chopping this up in a way that has one completely dominate. You don't get the proportional representation of 60-40. You get blue winning all the districts. And then you can do all kinds of interesting and complicated things where you are not fair and you are not compact, where you do these sort of jigsaw puzzle boundaries. This has gotten extreme, particularly the US is certainly not the only place that does this, but there's a lot of very extreme partisan gerrymandering in the US. Here it is an example of an actual district shown in red here, where there are really major disparities, very non-compact regions, and huge disparities in terms of the number of voters versus the results they get. If people are curious, let's actually click through. Is this going to work in, I believe this will work. So this is an older discussion of gerrymandering in the Washington Post, where we've actually grabbed that if people are curious about seeing this in more detail. they can, but I actually want to stick with the slides a moment because I preloaded the ones I care about. Here's an example from the New York Times trying to show some alternative maps where they are doing simulations of what could be possible and then how you could try to reduce the amount of gerrymandering. Notice how on the left they are proposing much more compact districts. The current map, which has some quite non-compact, quite bizarre spatial region districts, and then showing examples of what you could do if you were doing an extreme gerrymander to try to really pack the house for one versus the other. And just to follow up on this, there was in fact a court decision that mandated less gerrymandering, which then did affect the political outcomes. So the point that is relevant from a visualization point of view, this is not a poli-sci class, but that this problem of how do you aggregate spatially, it's something that can be deliberately gamed. It's something that doesn't have a perfect and optimal solution necessarily, although there are definitely criteria for making better versus worse decisions, including fairness and compactness. But as you saw in this example here, it is even possible to be compact but unfair. So fundamentally, this is due to this modifiable area unit problem, and it's one reason why spatial aggregation is extremely tricky, even if you have the same size districts. And once you go to different size districts, it's even more extreme. So for any of you who are doing anything in your final projects that do involve cartographic data or maps, you should definitely be aware, just like with choropleth maps, there's this huge problem that if you have different size spatial regions, you get quite a different sense of what's happening. This question of how do you break down spatial data, what region are you using? Are you using fine-grained versus coarse-grained? Are your regions the same size? These are all extremely tricky problems. Any questions on the spatial aggregation before I move on? Belatedly, I'm seeing a question about the foundation. Will the last foundation be 4% instead of 2%? Yes, because it is combined across both. So that last combined one will be a larger one. Okay, back to slides. All right, so let's talk for a moment about clustering, because clustering is a fundamental thing we have with when we're thinking about aggregation. So at the high level clustering, we can just define that simply as we're trying to classify items into similar bins. Yes, I see there's some stuff. Definitely doing the hand raise is great because it actually puts a little signal on mine. So also, and then I know who I can unmute if need be. It looks like the question was, can I repeat why spatial regions can be compact? Let me go back to compactness. If spatial regions are not compact, you can quite easily have extremely biased representations. So let me actually go, let's look at this example of an extreme gerrymandering. So in this one on the right, if you're allowed to basically have whatever shape you want, where you could say things like, well, here's some people that support one candidate, and then way over here are some people who support the other candidate, and there's the teeniest of tiniest of strips in between them, you can basically engineer things so that political power goes to the group that gets to draw that map. Because you could imagine that if you have people scattered around, you could either try to divide up where there is a group of people who all support the same candidate, like maybe divide up a city to keep the urban areas from having power, or you might try to put together some groups that do support a particular candidate, even though the region as a whole might support a different candidate. So once you're allowed to have non-compact regions, you can get very, very, very extreme in terms of these disparities, which is one reason that people typically are trying to have compactness. It's not the only criterion, as you could see here, where you can be unfair even though you're compact, but once you leave compactness as a criterion at all, things can get very extreme. Okay, so to get into the Zoom, the hand raise option is something that you can do if you go down to the bottom of your screen under participants, open up that window, and then there's a hand raise button that should be on the lower right of that participant window. Great. And so I'm trying to keep an eye on the chat window, but also it's even easier for me to keep an eye on the hand raise window. If people prefer typing questions like this rather than actually saying things out loud, that's fine. That seems to be working pretty well so far. But I'm also happy when there's a hand raise to unmute you. But you don't have to say, even with the hand raise, you don't have to speak out loud. You could use chat. Okay, so back to the slides and to clustering. So we just started talking about clustering. We can have the classification of items into bins. Typically, you can do that based on some flavor of a similarity measure. And so one way you can think about similarity measures is basically like a derived attribute, where you can say for every item, you can take a measurement between that item and every other item. You typically then get these n-squared data set sizes because it's pairwise distances between every pair of items. This is often things like Euclidean distance is a very common one, or things like the correlation between things. Things like Pearson correlation are another possible similarity measure. We're not going to go super deep into clustering, just enough to give you a flavor of that. One approach to this is to basically start from the top and go down, so to divide data into some set of bins. The challenge with that, a lot of you have probably heard of k-means clustering, is, well, how do you know what k is? The number of bins, is that something you know a priori? If so, fantastic. In a lot of data sets, you don't know that number a priori. There are algorithms for trying to find some reasonable thing, but that's one of the things that makes clustering very algorithmically challenging. For another approach is to actually, often starting from bottom, but to produce not just here are the bins, but a hierarchical structure where you have, these are often depicted as dendrograms. You saw an example of that kind of cluster hierarchy. Actually, let me check, yeah, we've got that one. I'll show you in a second. Some examples of that, which you saw with the heat maps. And so one common way to do those is with a bottom-up algorithm called agglomerative clustering, where you start out and you basically say, okay, if I have n nodes, I have n clusters, then try to merge the two closest ones and continue from the bottom up until you have a full hierarchical structure of these clusters with nested clusters inside of them. This sort of a cluster hierarchy is exactly well suited for showing data with any kind of dynamic aggregation. So what you'll often see in a visualization context is that you take some base data set and you construct one of these cluster hierarchies on top of the data set. Let me actually do that. And so with this, let me hand wave so that you can actually see my hands. So with the cluster hierarchy, what you get is a structure that can be used dynamically. One of the benefits of bothering to cluster, in addition to simply splitting the data into bite-sized pieces, typically within the cluster, you're more homogeneous than across the whole thing. And so you can do a lot where you do some sort of additional derived computation, like computing some statistical measure or computing the distributions within the cluster in a way that's actually going to give you more signal than if you just tried to do this across the entire data set. So let me remind you this idea of a cluster hierarchy. You actually saw this before when we were right at the end of the lecture on networks. We were talking about the idea that there was a base graph. So here at the very top, these light blue nodes. Actually, let me do a quick check. Can people actually see my cursor moving around on the screen? If so, do that little yes checkbox in the icon thing. I see some yeses in the chat. Okay, great. So we've got our base cluster graph. Sorry, we have our base graph, the light blue ones, and then we have constructed a cluster hierarchy on top of that. In this particular case, it's a visualization tool that lets you actually interactively decide how to structure that hierarchy on the fly. And the thing to notice is, so here's a representation of that cluster hierarchy where the nodes in the original graph are leaves in this cluster hierarchy, and then there are well, in a graph context, you often call these metanodes, the internal nodes of this cluster hierarchy. And in this case, with the Grouslock system that actually came out of my own lab a while back, we are explicitly showing that cluster hierarchy visually in the display. So the cluster hierarchy is considered a part of the data set along with the base graph, and what's being drawn in this view on the bottom is both the base graph nodes and, in this case, metanodes using containment to actually show this nested structure. On the top is a node link view of the cluster hierarchy. On the bottom, we're using containment to show the cluster hierarchy on top of a node link layout that's showing the base nodes of the original graph. Notice how in the top view that's only showing the cluster hierarchy, there's no information about the raw graph topology. So showing both the cluster hierarchy and the raw data can be one way to go. And the thing to notice is that in this case, which is also going to be the case for a number of the other ones we're going to look at, you can dynamically use this cluster hierarchy to decide the level of detail that you want to see things at. I see some questions here. You guys use the hand raise button more so that I notice when you have questions. Are clusters just nodes and links? No, clusters are, think of a cluster as a cluster is a set. A cluster hierarchy, however, actually does have internal hierarchical structure where you have clusters nested inside of clusters nested inside of clusters. So a cluster hierarchy is something that you do think of as having nodes and links, but a cluster per se can just be a set. So let's see what some of the answers are. Good? Okay. But just while you're asking that question about clusters, let me see if I can quickly bring up an example that might be useful. Let's if we can find Uber cluster speeds. I'm not sure if this search term is going to get me the aha. Yes, first hit. So this might be a useful example of here's something where this is actually some of the Uber speed data, and they're saying so. We have a bunch of different speeds that people were achieving on city streets, like over the course of, in this case, it looks like maybe one day from 6 a.m. to midnight. And so what they've done is they have clustered this data according to roughly shared speeds, and then they are showing these clusters on a geographic map. In this case, it's San Francisco. I wonder if I can make this bigger. Maybe I can. There we go. So the thing to notice here is this is a non-hierarchical clustering. This is simply saying there's a flat clustering, there's 6 clusters, 0 through 5. You can see in this visualization on the right that it's a sense of what these are basically, I believe it's 1 row per street. So you're able to see how fast people were able to go. And then they have mapped these clusters. So within the heat map, they're actually using, interestingly enough, they're using a diverging heat map, not a sequential heat map. So what they think is interesting here is there's a normal speed and there's fast and there's slow, just as opposed to saying it goes from a min to a max. And that is with this sequential diverging color map that goes from highly saturated pink on one side, highly saturated green on the other, to a neutral color in the middle. So that is the color coding of this heat map. Then notice how here they are depicting the clusters here sort of along the columns in basically a sort of built-in legend. And then in addition, they have a legend on the side here where they are color coding actual streets by these clusters. Now, one thing you can notice while we're talking about color is the fact that they've got this really light yellow cluster 0, and they're showing it against a basically pretty light gray map. Means it's quite hard to distinguish these cluster 0 streets from the background map because there's insufficient luminance contrast. So although Uber has a great viz team in many ways, they did not completely nail it on their choice of color for this graph. But what you can definitely see is this cluster 5 where things are very slow, and these cluster 4, these are the salient colors that are jumping out at you. For those of you who know San Francisco, this is basically where everyone gets on the highway in South Market, where all the tech companies are, and congestion is terrible. along with just a few other high traffic regions. So this is an example where the clusters are simply sets, but they are using those clusters to actually show the data. In this case, it's a multi-form approach where the clusters on one side are being shown spatially by color coding the streets on the spatial view on the left. I'd almost made this into a slide, and clearly I should have, since I ended up talking through it. All right, so going back to this idea then of, well, a cluster hierarchy, you might remember from a long time ago when we were talking about heat maps that we said, in a case of a heat map, these are some examples that are actually out of biology, where it's very common that the heat map is showing things like the amount of proteins that a gene is making. So it's called gene expression level. So basically how on a gene is. And it can be either upregulated, in this case being green, or downregulated, meaning it's producing many fewer proteins than normal, which would be red. The thing I want you to notice here is these dendrograms, that is, these visual depictions of the cluster hierarchy, are directly showing you the relationships between how is it that, because remember that we often reorder these matrix style views. So in this case, this cluster is showing you how the order was determined for these various columns to try to capture some of that structure. That's all stuff we've actually talked about before. The part that I want you to notice, which is new in this view, is this is actually just a few extreme close-ups so you can see what's even going on, where you've got this is the cluster dendrogram, you've got the heat map on the bottom and showing the dendrogram on the top of the clustering. And this interface actually lets you play around dynamically. That's what this line is here with. By moving that line up and down, you're basically saying, how much of the cluster hierarchy do I want to actually expose in the heat map? So by dragging this line up and down, you're basically controlling essentially the coarseness of the heat map. You could move this way up to see only a few clusters, or you could move it way down to see a very, very, very fine-grained view here on the heat map. So it's a very explicit way of having the cluster hierarchy visible, having the hierarchical clustering being a thing that you control directly as a way to have a level of detail for the other part of the visualization, which in this case is that heat map. Let's look at another example. Let's go back to parallel coordinates. Remember that with parallel coordinates, what we're doing is we've got these jagged polylines that are showing, instead of having a whole bunch of scatter plots where each point represents an item, we have these parallel axes, and the coordinates, you have values across all of these different attribute axes for an individual item, and the jagged line is showing you what an item looks like. When we did the scalability analysis of parallel coordinates originally, we said stuff like, well, once you get too many of these these jagged polylines representing items, they're just all going to be on top of each other. There's going to be a huge amount of overplotting and occlusion, and there's going to be too much clutter to actually see what's going on. So with this system, this is a hierarchical approach to parallel coordinates. What they've done is they've taken an original data set, which actually had hundreds of thousands of items. When they tried to just overplot them, let me grab this figure in particular so you can see the utter mess. Just like you can have hairballs with node link graphs, if you try to just directly look at this, the parallel coordinates plot, notice how when it's very sparse, I'm going to make this bigger so you can see it. So when it's very sparse, like here's a homicide data set where you've got 13 records, great, you can see a lot of structure. When you've got 16,000 records, you're essentially seeing almost nothing but, let me grab this over here. Almost the entire thing is overplotted. You can get a vague sense of the ranges, but you can only see individual lines at the extreme outliers, and almost everything else you can't tell the amount of overplotting here. So one approach to this could have been to do something like what you saw back with the continuous scatter plots. You could have said, oh, if there's a lot of overplotting, I could just use some sort of a density coding where the number of overplots I could actually color code. That would be one approach. That might actually show you some structure here, but they picked a different approach. The approach they picked with this one was they said, all right, let's use this idea of dynamic aggregation. And they did this same trick of computing a hierarchical clustering on the data set of these jagged parallel coordinate lines. So they tried to say, let's think of similarity as being essentially both the shape and position of these line segments with respect to each other, so that we can cluster whether two items, which are these jagged lines and parallel coordinates, are actually similar to each other. And they constructed an entire hierarchy of this. And then they said, let's start from the top and say, what happens if we take the entire data set, one big cluster, and visualize that? And that's what you're seeing on the left here. This one very large cluster, we're seeing there's a line that goes through that's basically, think of that as sort of a midpoint, just like the median on a box plot. And then you're seeing quite a lot of blur on either side of it. That's a visual depiction of how many items are, what's the range of all the items in that cluster. Notice how this picture on the left, in some ways, looks like the picture on the right here. I think it's the same data set. Yep. Actually, I'm not fully convinced that's the same data set. No, different data set. But you can notice some min-max ranges, like it looks like the second one of the year is getting almost all of it. You see that along these axes, it's not absolutely out to the min-max on every one of them. So you're getting a little bit of information. So they're actually color coding. The band of this has a opacity ramp where the line's at the mean, and you're seeing these min-maxes along this. Now, what they're doing as we go from the left view to the middle view is they're descending the cluster hierarchy. Instead of just being at the root of seeing only one single cluster for everything, they've said, well, show me the top, let's see, 1, 2, 3, 4, 5, 6. Show me the top 7 clusters. And with the top 7 clusters, we're using the same visual encoding of having the line through the mean and these min-max width values and this partial transparency. You're able to actually see a fair amount of structure. You definitely can see that there is this one cluster along the top that splits out that has quite different behavior than these other clusters. So you're starting to get a sense of the main signal in this data set that's being captured. Now, what you can mainly notice from this view is, well, they seem to have different colors somehow. It's not maybe instantly obvious what they're color coding by. Specifically, the color coding here is trying to be as vibrant and saturated as possible, since you're getting a lot of blurring from using transparency as well. And so they're trying to have maximally different colors. They're actually color coding by how close things are in the hierarchy. The intent here is not categorical color coding. You know, once you go to like 20 or 30 clusters, there's no hope of having individual distinguishable categorical colors. What they're trying to do is guarantee that if two things are quite far apart from each other in the hierarchy, that they will have distinguishable colors from each other. So the real thing they're trying to get people to notice is, hey, this tan line is a really different color than this cyan or this dark blue. These are distant in the hierarchy, whereas these two that are actually a very similar color of green, those are close to each other in the cluster hierarchy. So you can think of this like in some ways, a bending of the rules we've talked about. They are using hue for ordered data, but they really are trying to say maximal distinguishing of hue if you're distant in the hierarchy. So it's an, aha, raised hand. Let me actually unmute. There, you can now choose whether to either, no, that didn't work. How is
Hi.
my, oh, yes, working, great.
I was just wondering if you could explain what that purple line is there, because it
This
doesn't
purple
really
line here is here on the bottom?
yeah, because it doesn't resemble the yellow or the green to me.
Yeah, so I think what's happening with the purple one on the bottom is it is distinguishable only on this left axis where it's at, this is the state axis. So it's coming from a different state. It looks like this is a fairly categorical axis. And then it's actually merging with the rest of these. So basically, you've got a cluster structure that's along the bottom where essentially all of them are together and they're so overplotted that they're just going to a somewhat pale white and you can't see distinction between colors. And then over on the left, you actually see these break down into different states. And so we've got this 1, 2, 3 different states, but in this third state here, there's actually a split where some of the ones from this state then have this really different behavior on the year axis as opposed to the other ones which are going to this central point. Does that make sense? Or is it still mysterious? How?
Thank you.
There we go.
Yeah, but I was just wondering why it's purple. So if it's so similar to the green ones in behavior, why did it get colored purple? Is that just due to the clustering algorithm? You can't really tell why it's different color?
Well, let's actually go, let me flip over to that paper itself and zoom out a little bit so you can see. What they've done is, the proximity-based color coding is across the cluster hierarchy as a whole. So let me actually see if we can get this a little bit more visible. So what the purple is saying is it's sufficiently different from the green that it got a different color. I don't know that I can exactly talk you through why this is so different than these other two. That would actually, I think, require me to maybe flip around in the data set. So I don't have a direct answer, but the main point I wanted to make with this is, like, maybe this is a good example in the middle here, where in the first one we have only a single color, green. On the second one here, we essentially have 4 different colors, which are fairly different from each other, and then they all combine here when we're looking at the next level of detail. Once we're looking at more, we actually start to see things diverging. And then the main point I wanted to make is, even with actually showing quite a few clusters, you're able to at least capture some of the structure in the data. At some point, when you see too many clusters, then it's sort of almost back to the problem of seeing very little. But that there's this middle ground where we're able to see a fair amount of structure up to maybe a couple of dozen clusters that was impossible to see if we just look at everything.
Okay, got it. Thank you.
Yep. Okay. All right, so the main point on this one is the idea that we are using this hierarchical clustering as a way to control something like the level of detail dynamically. So that idea, so we've now seen a couple examples of this, but that big idea is something that you'll see with a lot of these more dynamic approaches. So last time we talked quite a bit about static item aggregation, and the box plot is your, box plots and histograms are classic examples of static item aggregation. Often dynamic aggregation has some sort of hierarchical clustering underneath it, which is typically derived on the fly by the visualization system and doesn't necessarily have to come with the original data set. Okay, so now let's move on to the last big topic of the day, which is dimensionality reduction. So what is that? And I'll often say DR for short. So dimensionality reduction is really a form of attribute aggregation. We have been really focused on aggregating items in a data set. So if you're thinking about a tabular data set, aggregating items is something that we're doing where it's sort of easy to think about. These items are somehow similar. I'm going to group them together. I'm going to have some proxy that stands in for a bunch of items. What does it even mean to aggregate attributes? Normally if you're thinking of your rows and columns, attributes are columns in a simple table. How could you possibly aggregate across columns and have that mean anything? As opposed to, earlier when you were doing some of your sketches and we had data sets and we had things like, how long it took you to run in the race versus how high could you jump. we explicitly told you to be careful when you were visually encoding that you didn't somehow imply that these two things could be directly compared to each other. These were completely different attributes with probably completely different min-max ranges, different semantics. So if we've just spent all this time being so persnickety about attribute semantics, how is it that we're now telling you you could somehow aggregate them? So let's think through what kinds of data sets this would even make sense for. We take this kind of approach when we have very high dimensional data, anywhere from, say, this example is 9 dimensions, but we can go up to, say, tens of thousands of dimensions, where we have very, very, very high dimensional data. And we suspect fundamentally that what we have has internal structure that is way more compact than the way we happen to measure it. Typically, the way you think about this is sometimes you can't just measure what you want. In the case of the races, you could just measure how far they jumped. You can measure how long it took them to run the race. But there's a lot of quantities you would love to know the answer to that you can't just measure. Instead, you can measure things that might actually be very, very redundant with each other, that don't directly, so your measurements could be very, very verbose. Let me actually say what the example is. Let's take the idea of you've got a tumor. You've got some sort of tissue sample, and what you want to know is this malignant or is this benign? But we don't have an instrument that just tells you that answer. Instead, we have instruments that allow you to measure things like, the density as certain kinds of radiation pass through it. The things we measure are not just the answer. They are measurements that might be able to lead us indirectly towards an answer. And so the idea is there's many of these kinds of data sets where what we think of as the true dimensionality of the data set is much, much smaller than the dimensionality of the things you can easily measure. So the example here is we've measured 9 dimensions of things that are actually capturable with tumors, and we conduct this dimensionality reduction approach, and now we're looking at a scatter plot where even if we hadn't color-coded it according to ground truth, in this case we've color-coded according to whether we figured out later was this malignant or benign. So those classes in the data are color-coded. But notice how the positions of the points in this scatter plot in this new 2-dimensional space are actually capturing that structure. We're seeing a really dense bit on the top right, and we're seeing a much looser bit on the bottom left, and that is corresponding to this classification of malignant versus benign. So the layout in this new target space is actually capturing this what's often called a latent structure. Sometimes these are called hidden variables or latent factors. If you've got a machine learning background, you might have heard these words used before. So the way we're doing this algorithmically, this class, we don't have time to get into the algorithms on this, although it's fantastic, and if you're interested, it's a super, super interesting area. I'll just content myself with saying that there is quite a lot of algorithmic work that is trying to do this idea of capturing the variance across the original high dimensional space in a much, much lower dimensional space. So these new low dimensional space that you synthesize algorithmically, you can think of as new attributes, new aggregated attributes. Let me give you another example of this kind of an idiom, and we're actually going to think about chaining some tasks together. Let's say that you have a data set of 40,000 documents. And, well, you want to know what's going on. Are you going to read all 40,000? Maybe that would take too long. So dimensionality reduction is very commonly used for these kinds of very high dimensional spaces where you think of each document with what's called the bag of words model. So we're actually going to construct a really, really, really huge and sparse matrix where every item in this table, so every item is a document. And then what we're going to do is we're going to take the set of all words used across all of the documents. And that's going to be a lot. There's probably tens of thousands of words. So you might have 40,000 documents, and you might also have something like 40,000 words. And each time, and you just keep a count of each time a word was used in a document, and that's actually what you're putting in as values. So you've got a huge table where the items are documents, the columns are words, and you have per word count for the document. Now, this so-called bag of words model, you've lost a lot of the structure of the document. You've completely lost, for example, did this word occur in the same sentence? You're actually aggregating things down to the level of across the whole document, how many times was the word kangaroo used? Now, from a visualization point of view, do we want to try to directly visualize a 40,000 by 40,000 table? That's going to be chaos, right? There's no way we could possibly do that. So what we want to do is derive a new table. And that new table, we're going to say, can we capture most of the structure in that very high dimensional space in a much more compact space? We're going to try to go down to just 2 dimensions. And that's what we've got with this first task on the left here, where we've said we're going to synthesize 2 new attributes, 2 new dimensions using DR. Because it's called dimensionality reduction, I'm often going to talk about attributes as dimensions when I talk, just for this part, even though in general we've been calling them attributes. So we synthesize these 2 new dimensions, and then we've got a table that we have a hope of seeing. Then we can use existing well-known idioms. For example, we could just plot the items in these 2 new dimensions as a scatterplot. So we're taking an idiom that's known as scatterplot, and we're using it on this dimensionally reduced data where we've synthesized these 2 new dimensions. And we can try to say, hey, is there cluster structure? Does it seem like this bunch of documents might actually be related to each other? So we can go ahead and we can visually encode this with the scatterplot. Typically, in order to actually make this useful, you often need some way to explicitly query an individual point. Like possibly if you click on the point, it's going to actually pop up the document. You take a quick skim, and you might start understanding, oh, maybe I can propose a label for this cluster. There are automatic methods that try to come up with labels for cluster. This is often called topic modeling. These methods are still very far from perfect, so you often need some human to actually go in and check, because NLP, natural language processing, is not usually at the point of being able to get fantastic labels for these clusters automatically. But this process of dimensionality reduction can actually create these spaces where a human really can go and look and try to understand, do I believe that this group of points that are clustered together actually is capturing some sort of semantically meaningful structure in the original data set? In this proposed pipeline, maybe what you do at this point is actually annotate that cluster with a label. Based on this sort of inspection, that's one thing that's possible. So let's actually go into this a little bit more. Why do people actually use this? There's typically a real divide between using it in a machine learning context and using it in a visualization context. So often in an ML context, you might simply be using dimensionality reduction. Yes, hand raised, 1 sec. Go. Okay, so this is a chat. Tamara, can you comment again about the variance you mentioned that we're interested in? Is that with respect to a given column? Yeah, so the variance that we're interested in is, and let me actually go back to, well, let me go back to this picture. We're trying to say that there might be, the very simple case is that a column might be very, very low variance, and then you could just throw it away as being basically not meaningful. But the variance that we're often talking about is it could be that essentially there might be many columns that are basically very, very similar to each other. So you can sort of think of the columns as really having measured the same thing very, very redundantly. So when we think about capturing most of the variance, we aren't just saying within a single column. We're saying that if many columns are similar to each other, we might be able to capture that with this aggregation where we sort of aggregate all of those columns together and have a proxy column. Does that help? Okay, so yes, answered that first question. And then there was another question, which was on the previous page in the task 1 box, that would be this one. What would be the 2 dimensions in the output? So basically the 2 dimensions in the output is these 2 dimensions that you're plotting in the scatter plot. These are 2 new dimensions you can think of as actually being in a new two-dimensional space. So all of the items from the old high-dimensional space you can plot in this new two-dimensional space and try to decide if it's even meaningful. So this question is, so do we arbitrarily choose what we want to see? Well, what we do is we are running an algorithm that's trying to do a good job of capturing as much of the structure as possible. So the algorithm's not trying to be arbitrary. The algorithm is trying to actually capture that variance in these two new synthetic dimensions. Okay. Was there a question about bag of words in particular? And also I'm unmuting Mohit. I think you've got a question.
If Andy is finished, I'll go ahead.
Okay, Andy done. Over to Mohit.
The question I had is, if dimension 1 and 2 are the two axes through which we would plot something like this, I'm trying to figure out what the higher dimensions would be such that we get to 1 and 2. So what exactly are we aggregating?
Right. Let's put that question on hold for a moment while I actually show you a bunch of examples. I think that might be instructive because this is all super, super abstract. So let's try to look at a few examples and talk through it. And if you still have that question, then re-ask it after we get through a few more slides. Sound good?
Yep, thanks.
Because right now it's super abstract. Okay, so So we're about to see some examples. So, but the point I want to make is just sometimes in an ML context, what people do is they just try to go from, say, 100 dimensions down to 20 dimensions to have algorithms that work in a reasonable amount of time. So they're using it purely in order to take something and put it into an algorithm. But with a visualization context, in any sort of visual data analysis, what we're typically doing is we're doing DR, and then a person is actually looking at it to try to come to some conclusion about their data. And that's the use that we're going to be thinking about today. And so mostly what people are that F equals MA comment, not quite. Let me get to some concrete examples and then see if that answers. So typically what they might be doing is they might be trying to understand these new synthetic dimensions that just got computed. Do they have meaning? Can I come up with a name for them? Do I understand the relationship of the new dimensions back to the original ones, which gets at, I think, one of the questions that just got asked. And another thing people do very often is they try to understand whether the cluster structure they see is believable. So do they actually see cluster structure? Can they come up with some semantically meaningful name for the cluster? If they have some idea of an existing class, is that class actually matching up with the visible clusters, or is it cross-cutting? So let's go back to something a little more concrete. Let's say that you've got an image data set. So these are some of the examples from some of the algorithmic papers talking about these dimensionality reduction approaches. So here we've got a whole bunch of points. Each one of these points represents a picture. Now, a really silly, in some ways, way to think about a picture is as a very, very high dimensional data set, where for every pixel in the image, you think of that as a separate dimension. So all you know for that pixel is it's got, in this case, maybe it's a grayscale value, maybe it's a color value. So you have this really high dimensional data set that you think of as an image. And then you think there's got to be some structure in here that's not just blindly treating every pixel as separate. Can we run these algorithms and actually capture that structure? And here's an example where they were able to capture that structure. And what they had was this was not just a random collection of images. This was a collection of images where they took pictures, in this case of a statue, I think, from a bunch of different points of view of the camera, of where the camera was pointing at compared to the person's face. And then they also had a bunch of different directions that the lights were coming from. So this dimensionality reduction algorithm was actually able to find that structure and capture it. So these here's a case where these axis labels of the up-down pose of the camera, the left-right pose of the camera, the lighting direction, that's actually something that was captured by the DR algorithm from treating this as just basically a bag of pixels in the image. So that's one example of, and then people actually went through and they tried looking at these and said, a human assigned the labels to this axis, but the algorithm came up with these axes in the first place. Here's a different example. Again, we're looking at images. In this case, the images are of people doing handwriting of digits. These digit data sets have been heavily used in machine learning to try to understand a bunch of different things. So here we're actually seeing, here's a bunch of different ways to draw the letter 2. And when you go in and actually plot these and then start looking at them, you see that a human can add a label to this axis basically saying how much does the bottom loop actually have a squiggle in it as opposed to being flat. That's what that bottom loop articulation thing is horizontally. And then the top arch articulation, is basically how curly is the top part versus not very curly at all. So not curly at all on the top for the top parts, and then on the bottom, very, very squiggly tops. So these were two concrete examples of, you had this high dimensional data set that had a lot of structure that was very, very redundant, and you were able to capture something much more compact that actually had semantic meaning when you ran these algorithms to compute the lower dimensional structure. Let's look at another, so that's an actual concrete example. Let me now unmute to check whether that has actually answered some of these questions about the new synthetic dimensions can be dramatically different from the earlier one. I'm not sure what the F equals MA question was, but I believe that that's not typically what you would do. I can't quite tell what you're asking. Okay, well, that one didn't get re-asked yet. Let's keep going. Definitely okay, all clear, great. So this was examples of trying to understand what the dimensions mean. But I said there was another thing people might do. Like you might say after you've got dimensionally reduced data, you might not see any cluster at all. Or you might see really clear clusters. Or you might have some idea of a class structure and you want to know, did the clusters match up with the classes? Here's one where if you color code the classes and you look at the clusters, you see, oh, that really aligns very well. But like here's an example where no, in fact, the color coding does not match up with the visible cluster structure. We can see that there's one case where the class is split across 2 clusters. There's one case where we don't at all get any kind of nice separation between the class and the clusters. And then you might have something where, it's just, and yet you do see that there's something, right? You only see the red dots in 2 of these clusters. It's not a complete mismatch, whereas on the far right, we see basically a fundamental mismatch where there's really no alignment at all between the visible cluster structure in these dimensionally reduced scatter plots and the class structure. This whole sort of taxonomy of understanding what people are doing actually came out of some work from my own lab where we went and talked to a whole bunch of people doing high dimensional data analysis to try to understand what their underlying tasks were. So let's talk just a tiny bit about these algorithms to give you some visceral sense of them. Again, there's a lot more depth we could go into if we had time, but we're mostly focused on this from a high level today. The thing you're going to hear used quite a lot is the most obvious and famous and old dimensionality direction algorithm is PCA. That's called Principal Components Analysis. And what you're doing is PCA is you're basically trying to say, hey, I want to find an axis that captures as much of the variance as possible. And I'm going to call that my first principal component. And then you keep going and you say, okay, is there a second principal component? And it's really easy to think about in this case where I've just got a Gaussian blob, right? So if I've got a nice sort of 2D Gaussian distribution here, PCA does a great job of capturing this because essentially you can say, oh yeah, look, there was one axis that seems to be the major axis of this little ellipsoid. And I can say, okay, here's another axis of that. And I've captured one sec, let me get some water. Okay. What was I talking about before I was coughing? PCA axes, right. So you captured essentially a lot of the underlying structure in this very compactly by saying I can talk about the length along each of these axes and do a pretty good job of describing this data set. What's also nice about PCA is that you are able to really easily map between the new synthetic dimensions, which in this case are these two axes here, versus the original dimensions. It's actually a linear weighted combination. So PCA is great if you've got a bunch of simple Gaussian blobs, but in the real world, data is often a lot more complex than that. So there are many other approaches that are trying to capture more complex structure. Rather than just lines, you might have things that in the high dimensional space are maybe more curved, so nonlinear. Most of these methods don't do a great job of being able to map back to the original dimensions, so it can be difficult to understand any sort of back mapping or back projection. So that task of understanding the relationship of these new to the old dimensions is not necessarily easy. A lot of people have approached this problem. There's actually a whole bunch of different research areas, visualizations read about this, machine learning, optimization. It actually originally came out of psychology as a way to try to understand data about way back about human perception back in the earlier part of the 20th century. These days, the modern techniques that people use, there's a number of them. TISNE and MDS are some of them. There's also charting and isomap and locally linear embedding. The more modern techniques are really often trying to capture a lot of this cluster structure. One other thing, it might not be crucial for you to know, but there's a lot of different things that are all called MDS, multidimensional scaling, and some of them are even equivalent to PCA. That's sort of a nuance you don't have to worry about so much. Let's look at some actual examples of this. So this is this MNIST data set, which is basically how people handwrite numbers. This is a very common benchmark data set. And here are some examples of how different algorithms for trying to capture, in this case, they're all saying, let's just capture two-dimensional structure. What do these different scatter plots look like? On the left, we have this multidimensional scaling, which is basically treating the entire thing like an optimization problem. Notice how we're seeing a little bit of structure, but they're actually there's not so much visible structure here. Notice how PCA is doing really not a very good job at all of capturing these clusters. Right now, these are color-coded according to the digit. So this is trying to visualize the digits 0 through 9. And both MDS and PCA are failing to capture structure. Some of these alternative algorithms are actually doing a much better job at synthesizing these new synthetic dimensions that do capture a lot more cluster structure in the data. Both TISNE, which has been quite popular the last several years, and UMAP, which is brand new, that just came out, I believe, last year, that's doing a very good job of capturing this cluster structure. If people are at all interested in this, here are 3 very readable and useful walkthroughs to try to understand what these data sets are. So these are, the first of these was sort of early work in trying to understand these computer vision data sets of visualizing the numbers and how these things are laid out. I'm not actually, but the key thing I want you to notice is they actually show you these algorithms in action. Here it's processing the math. There we go. And notice how this is an example of, as I actually put my mouse over one of these points, we can see what it looks like. So this is in fact an interactive app that does let us do this. It's very common that when you look at this kind of data, you need some way to query. When the original data is an image, it's pretty trivial and easy to query with the pop-up. When it's an entire document, of course, it gets a little more complex. It can be even more complex when the items don't have a really easy to capture visual structure. But this one we're able to see, okay, looks like all these purple ones are 7s, maybe these red ones are 0s. So we are seeing some cluster structure with the 1, but it's not ideal. For those who are interested in Understanding TISME in particular, this is a great post that is in a, this is a journal that is an online journal that's very, very heavily focused on visualization, where all the articles are a mix. This is actually from the folks at Google Brain and Google Cloud. And essentially all of the articles involve directly embeddable visualizations as part of the exposition. So this is sort of a new experiment in how people can understand things where visualization is a key part of that. So if people are interested, Distill in particular is focused on machine learning. And so it's a bunch of these visualization articles to try to help people understand a lot of very specific things in ML. So pretty fantastic resource. Also, if anyone is interested in continuing on with these sort of visualizations beyond this class, this is a great thing to have a look at for some inspiration of what kinds of things are possible, especially if you have any interest at all in machine learning. And similarly, there's another one from the Google group about understanding this new UMAP algorithm that is similarly helping people actually walk through. I'm not going to take the time to walk through it in class now, but it's sort of an explainer trying to help people understand some of the algorithmic aspects of this. I've been taking a little longer than I should. So I wanted to talk in a little bit more depth about this example. Maybe what I'll do is get through this while DR is in your head, and then wrap up and cover the rest after. So just to give you yet another concrete example of dimensionality reduction, here's one where people again have these very large image databases. In this case, they actually have an all-black room where they have a calibrated light source and a little ball of some specific material and a camera. And they take a whole lot of pictures of this object from the different positions of the camera, the different positions of the light source, because they want to exactly know how light bounces off. For those of you who've had a computer graphics class, these are called BRDFs, bidirectional reflectance distribution functions. And it really is a way to capture how objects work. And so they had this data set where they had 104 of these very high-res pictures of how the sphere has light bounce off it in this calibrated room. And each of these images is actually 4 million pixels, so very high-res things. And what they wanted is to be able to actually use all this data when they're rendering new pictures. But you need some kind of model that's not just like, let's take this 400 million dimensional model, because 104 materials and 4 million pixels per image of each material, you can't work with that. That's this incredibly verbose high dimensional data set. You want something much lower dimensional that you can actually think about. And they use dimensionality reduction so that they could try to have things like, I want it to be shiny or greasy, not just like, pixel 117 in image 47 should be this much more blue. You can't work with that. What's interesting from a dimensionality reduction point of view is if you just use PCA on this data set, one of the things people often do when they're working with these kinds of data sets is you don't necessarily reduce to just 2 dimensions. You might reduce to a larger number of dimensions. So for example, here's a case where they reduce to 45 dimensions. So you're no longer just looking at individual scatter plots. But 45 dimensions is a lot better than 400 million dimensions. And you can do these scree plots, what these are called, these sort of hockey stick plots, where you're plotting the number of dimensions, synthetic dimensions that you create versus the amount of error in the data set, the amount of variance that you're not capturing. And as you fall off, you start to think, oh, maybe my new synthetic dimensions are doing a pretty good job of capturing this data set. But then when they went and they tried to make pictures, they used this model and they tried to do computer graphics. Here's a picture of a teapot where they're just focusing on these specular highlights, the little shiny parts. And you have specular highlights, little shiny circles on real-world images. You can't have a black hole in the middle of a specular highlight. That's just not physically possible. In the real world, if there's a shiny spot, it's an entire shiny spot. It's not patchy. You don't have weird black holes in the middle. So they didn't have a good model. This model did not capture, if they just used PCA, linear dimensionality reduction. So they used one of these more sophisticated approaches. This particular one is called charting, as opposed to TSME or MDS or ISOMAP or any of the others. And when they use this other approach, they can again try to plot the amount of variance, non-captured variance or error against the number of new synthetic dimensions. And when they did that, they ended up with being able to actually more usefully see what was going on. So this is an example where then they plot every one of these pictures and try to look at these axes and figure out what's going on. And they found that actually they could say, oh, this looks more metal-y and this looks more foam. And they actually had people inspecting these and trying to understand what the structure was. And they found that they really did have these semantically meaningful dimensions that the algorithm had come up with that the humans could name, like how shiny it was, how much like a chalkboard it was, how glossy it was. So they were able to use this dimensionally reduced data to check whether their model was actually reasonable. Okay, so that is a good stopping point for today. I will cover the rest of the slides next time. And what I will be doing is that a hand? Well, that's a clap. Thank you. So I am going to cut over to office hour mode in just a couple of minutes. I'll take a quick break, reopen the Zoom window at 3:30 in the other mode, which is waiting room mode. And also remember that if you want to talk on some time that's not the office hours, because you happen to be busy then just send me email, and we can also use Zoom to chat by then. So we will be holding the office hours on Friday. We do not have anything due this Wednesday because this is chaos week while we all try to adapt. I hope all of you are staying healthy and happy, and I will see you all again on Thursday by Zoom. Bye-bye.